Hello, Vital Sign. Today we're going to talk about the non-complete extended p-sum of graphs, abbreviated as the NEPS of graphs. The NEPS is a very general graph operation. As its inputs, it receives an ordered list, also known as a tuple, of undirected graphs, as well as a set of binary tuples, that is, tuples whose elements are either 0 or 1. This set of binary tuples is called the basis. The binary tuples must be of equal size to the ordered list of graphs. That is, they are both n tuples for a positive integer n. In the demonstration seen here, n is 3. The output produced by the NEPS of some ordered list of graphs with some basis b is an undirected graph with vertex set equal to the Cartesian product of the vertex sets of its input graphs in the order they were given. Generally, two vertices in the output graph, each represented by an ordered list of vertices from the input graphs, are adjacent in the output graph when we can find some binary tuple, little b, in our basis uppercase B, such that for each index between 1 and n, v sub I is adjacent to w sub I when the ith element in little b is 1, and v sub I is the same vertex as w sub I when the ith element in little b is 0. Keep in mind that v sub I and w sub I come from the input graph g sub I. To make this a bit clearer, let's define the concept of a distance vector. If we have two vertices in some graph, we can denote the distance between them like this. We define the distance from one vertex to itself to be 0. Now let x and y be two vertices in the NEPS of some ordered list of n graphs. Then, as we know, x and y themselves represent ordered lists of vertices from the input graphs, where their first elements come from the first input graph, their second elements come from the second input graph, and so on. The distance vector, d of xy, is defined to be an ordered list where the ith element in the list is the distance between the ith element of the ordered list represented by x and the ith element of the ordered list represented by y in the ith input graph. With this in mind, let's return to the concept of adjacency in the NEPS of graphs. Our basis, b, can be thought of simply as the set of acceptable distance vectors. Take any two vertices from the NEPS. If their distance vector is present in the basis of the NEPS, then those vertices are adjacent. This is equivalent to our first definition of adjacency for the NEPS of graphs. What we have seen so far is that the final graph depends upon three factors: the choice of basis, the order of the input graphs, and the input graphs themselves. However, what I've shown you is not quite the final definition of the NEPS. There is one restriction on what binary n tuples we can choose to be in our basis. We are not allowed to choose the tuple that only contains 0 at all indices. Now, before we work through some examples together, let's do a quick recap of the NEPS. NEPS stands for non-complete extended p-sum. The NEPS takes as its input a tuple of undirected graphs, as well as a set of binary n tuples. The NEPS outputs an undirected graph with vertex set equal to the Cartesian product of the vertex sets of its input graphs, in the order in which they appeared in the input tuple of graphs. Here is our first definition of adjacency in the NEPS. And then we have our newest equivalent definition of adjacency, which is that two vertices are adjacent in the NEPS if their distance vectors are elements of the basis. Now let's work through two examples. Suppose we have three graphs, G1, G2, and G3, with vertices in the first graph labeled with letters, vertices in the second graph labeled with numbers, and vertices in the third graph labeled with special characters. These are the same graphs we used before, in our first illustrative example, but this time they're in a different order and with different labelings. What is the NEPS of G1, G2, G3 with basis 001, 010, 101? Note that this is the same basis we used previously as well. First, find the vertex set. That would be the Cartesian product of the vertex sets of our input graphs in their given order. Next, look for vertices with distance vectors that match some tuple in our basis, B, and connect these vertices to each other. To do this, let's examine each distance vector in our basis, starting with 001. What this distance vector really represents is when your two vertices have the same first element, or letter, same second element, or number, and adjacent third element, or special character, in their respective input graphs. What pairs of vertices in this NEPS graph meet that criteria? Feel free to pause the video and find them yourself. Here they are. Specifically, if you look at vertices A1 asterisk and A1 hash, they meet this requirement as their first and second elements are the same vertices in the first and second graphs, meaning that the distance between their first elements is 0 and the distance between their second elements is 0. And their third elements, asterisk and hash, are adjacent vertices in the third input graph and have a distance of 1. So A1 asterisk and A1 hash indeed have distance vector 001. Now let's look at the second distance vector, 010. Vertices with the same first and third elements, but adjacent second elements, will have this distance vector. I encourage you to find and connect all pairs of NEPS graph vertices that have this as their distance vector. Here are the new edges. Finally, let's look at the third distance vector, 101. Vertices with adjacent first elements, same second elements, and adjacent third elements will have this distance vector. Again, feel free to pause and connect all pairs of vertices that have this distance vector yourself. Here they are. This is the final result. Let's move on to our second example. This time, let's operate on two graphs only. Suppose these are our G1 and G2, and our basis is this. Next, find the vertex set. Now examine our basis. We only have a single acceptable distance vector, 1, 1. Vertices with adjacent first elements, or letters, and adjacent second elements, or numbers, will have this distance vector, and will therefore be adjacent in the NEPS graph. What pairs of vertices meet this criteria? Feel free to pause the video and connect all pairs of NEPS graph vertices with both adjacent letters in graph 1 and adjacent numbers in graph 2. Here they are. Interestingly, this is the exact same graph as the tensor product of G1 and G2, shown on the bottom. Indeed, the NEPS operation on two graphs with basis consisting of the binary two-tuple 1, 1 is the exact same operation as the tensor product of graphs. To review, the tensor product's vertex set is also the Cartesian product of its factor graph's vertex sets, and two vertices in the tensor product are adjacent if and only if their left and right entries are both adjacent vertices in their respective graphs. Already we can see one use of the NEPS. The operation encompasses certain graph products. It's not just the tensor product that can be expressed through an NEPS operation. So can the strong product and Cartesian product of graphs. Pretty cool that we can represent graph products through this more general operation, the NEPS. I'll leave it to you to show the equivalence of the NEPS operations with the parameters shown here with the strong and Cartesian product of graphs. Now, what is one product that does not fall under the NEPS? That would be the lexicographic product. To recap, here are the adjacency conditions for the lexicographic product of graphs. Note that these conditions allow for two vertices, uv and u'v', to be adjacent in the product, yet have distinct, non-adjacent right elements. It is the first adjacency condition that allows for this. The distance vector for such vertices must contain right element greater than 1 or undefined, as the right entries, v and v', are distinct and non-adjacent, meaning they have distance at least 2. Since acceptable distance vectors in any NEPS operation consist only of 1s and 0s, such adjacencies are not allowed by any NEPS operation. So the lexicographic product of two graphs cannot generally be expressed through an NEPS operation. That's it for this video. In my next video, we'll take a look at clique polynomials. Thanks for watching. Please subscribe, like, share, and comment if you liked the video. Have a great day.